Ja, precies.
So first of all, Dutch or English?
English, please.
English, no problem. So I am Johannes de Boer. I'm a professor at the physics department, and I develop new imaging technologies for the hospital. And part of the imaging techniques that we use is Raman scattering. So my lecture today will be about Raman, cars, and stimulated Raman scattering. To start, oh, now it doesn't progress. Oops, how is this possible? So what you're all familiar with probably is elastic scattering, and that's what happens in a cloud, in tissue a lot. As Dirk has talked about, it needs to come in with a certain wavelength. That light is scattered. That means it has a change of direction, but the color or the wavelength of the light is preserved. We call that elastic scattering. And elastic scattering occurs by a change in the electron cloud around an atom or a molecule. So you have your electromagnetic wave coming in. It's an oscillation of the electric field of the magnetic field. You have a molecule with the electrons around it, so that's a charge. So the electric field will try and distort the electron cloud. It will bring that cloud in oscillation. But the effect of an oscillating charge is that it starts to generate electromagnetic waves itself. A moving charge generates an electromagnetic wave. So elastic scattering, if you go down to the atomic or the molecular level, is caused by an electromagnetic wave coming onto the molecule. The electron cloud around the molecule starts to oscillate in response to this electric field, and this moving charge generates a secondary electromagnetic field that is radiated out in all directions. Well, this is called elastic scattering because there's no energy transfer from the electromagnetic wave to the molecule. And so the oscillating electron cloud loses its energy by radiating out that same energy. In 1923 to 25, theoretical physicists Smeckhoff, Raman, and Heisenberg postulated that there also might be another mechanism of scattering, an inelastic form where there is actually energy transfer from that electromagnetic wave to the molecule itself. That means that there's energy loss, so the molecule radiates out part of that energy, but energy conservation dictates then that the radiated photons, so these electromagnetic waves, have a longer wavelength or lower energy. And that process of transferring energy to the molecule itself is called inelastic scattering. So it means when you transfer energy from the electromagnetic wave to the molecule, you excite electronic states in the molecule, vibrational levels in the molecule, and on a quantum mechanical level, you excite quantum states within the molecule. But at that time, it was not described what kind of energy transfer this was, or how the molecule would take up this energy. But as you will learn from the lecture today, the molecule takes up this energy in the form of a vibration. And you can imagine immediately if you have a molecule that consists of two atoms, then there can be internal energy in this molecule by, let's say, the two atoms moving like this, like a spring, where the electromagnetic charges make sure that the molecule stays together. It's an internal vibration of the molecule. Okay. Oh. And so this effect, and we'll get to that, was discovered by Raman. He was an Indian physicist, and he was at a conference in Europe, and he was fascinated by the blue hue that he saw when light was scattering of ice crystals and ice rings. And so, fascinated by this scattering phenomena of light, he established a research group in India to study these light scattering phenomena. And in a remarkably short time, he received the Nobel Prize for it. I think a few years after the publication of the original paper. I think I have it here. Yeah, this is the original paper. Nature, 1928, the first description of this Raman scattering effect. And so 2 years later, he received the Nobel Prize for it. If you compare that to the Higgs boson that was predicted in 1964-ish, 1960s, and it was discovered or finally experimentally demonstrated this century. So that took more than 40 years before the person that discovered the Higgs boson finally got the Nobel Prize. And in a way, Raman was lucky; he got it within 2 years. So let's look a little bit closer at that scattering effect. So it's an energy transfer from the laser or from light onto the molecule. And so, like I said before, you can imagine that with a molecule that consists of two atoms, you can view this as an internal vibration of the molecule. Part of the energy is absorbed then by the molecule, and the remainder is scattered out in form of radiation. And because the energy conservation, that wavelength is of a longer wavelength, lower energy. Okay, so let's take a look at these Raman spectrum. So here you look at a very simple molecule. It's a carbon with 4 chlorides around it. So it's a 5-atom molecule. And when you shine light on it and you measure then the spectrum that comes off, this is what you see. So you measure the spectrum by sending the light into a spectrometer. Yes?
Sorry, I think the PowerPoint that is posted on campus is not the same PowerPoint. Is that correct?
Oh, it could be because I think this is the lecture that Dirk told me to be given on Friday.
Yeah, I just posted. So if you refresh the top of down to it.
Okay.
Oh, Dirk is already modified.
Oh, really?
Working on it. So what you do is you take the light, you send it in the spectrometer. Spectrometer separates out the wavelength into different colors by sending them in different directions. You refocus that light on a sensor, a CCD. And in those days, these were photographic films. So we're looking at the spectrum of photograph displayed on a photographic film. And along the horizontal axis, you see wavelength, and and the intensity is given by the whiteness of the image. So what you immediately see is that there's a very strong line here in the center, and that is the original light that falls onto the molecule. But if you then look carefully around the center line, you see here 3 lines, and you see very vague also 3 lines on the other side. That means that the molecule is sending out radiation of a different wavelength as a consequence of sending this original laser light, or in this case a mercury light onto the medium. And here I've shown you now the graphic display of the intensities that you see here. You see here the center wavelength that is scattered, that is the Rayleigh wavelength, and then on the sides you see small peaks for wavelengths of a longer wavelength. But interestingly enough, you also see them of a shorter wavelength. What does it mean when there's a shorter wavelength emitted by the molecule? Is that possible? What needs to happen for that molecule to send out light of a shorter wavelength?
I guess it would need to decrease its own initial energy level to a lower state.
Exactly. It's the reverse process. So instead of exciting a vibrational state of the molecule, what happens is the molecule is already in a vibrational state, and the incoming light, together with that vibration energy of the molecule, you can produce the wavelength of a shorter light of a shorter wavelength. So there's energy transfer from the molecule to the light. So what we see here on this side, the shorter wavelength, that's the process of energy transfer from the molecule to the light that's being emitted. So What do you think is needed for that process to take place? If the molecule is frozen, doesn't vibrate, do you think it's possible? No, it's so the molecule needs to vibrate. It needs to, yeah. And what makes a molecule vibrate? Heat, yes, temperature. And so only at very cold temperatures, at the minus 273 Kelvin, you freeze out all internal energy states of the molecule. But as soon as you warm a gas up, the molecule, part of the energy is in the velocity of the molecules, and another part is in the vibrational levels of the molecule. It starts to vibrate. And you can immediately imagine, let's say you have a molecule that consists of 2 atoms, and it bounces off another atom that has a molecule that has 2 atoms. You can imagine that in that collision, part of the energy in the collision is transferred to a vibration of the molecule. If you look at the intensity of these lines, what do you observe? Which lines are more intense? The lines at the lower wavelength or the lines at the higher wavelength? At the lower wavelength. And because the peaks are higher, so there's more intensity in that lower energy. But there is also intensity in the higher wavelength. But what do you observe if you look at the intensity as a function of how short the wavelength is that's being emitted? Where again, this side is shorter wavelength, this one is longer wavelength. Are they equally strong? And I exclude you for a moment. I want to hear somebody else. Which line is stronger? This one or this one? Sorry? Yeah, this one has a higher intensity than the others. What does it mean that when this line has a lower intensity? What does it mean for the internal states of that molecule? If the molecule is frozen, can this process take place? No. So, what is needed for the molecule? It needs to vibrate. Sorry?
It vibrates less than.
Yes, or if you look at the quantum mechanical picture, that vibrational state has a lower occupancy. And so if you look at the molecules, you take 1,000 molecules, how many of these molecules are in a higher vibrational state? Let's say 50%. Well, if it's 50%, then this process at this side will have equal probability as the process on the other side. There's an equal probability of transferring back the molecular energy to the radiation, or absorbing the radiation and exciting the molecule. But if the vibrational occupancy is only 10%, what do you think will happen with the ratio of the intensity of this line and this line? It will shift, yes. Then this line will become stronger because you have a 90% chance of exciting the vibrational state, and you have a 10% chance that the vibrational state is converted into the photon energy that's being emitted. How does the occupancy of these vibrational states depend on temperature? This is an energy step, huh? From this to here. This is an energy step. It's the amount of energy contained in a single vibrating molecule. So to be able to excite that molecule in a vibrational state, I need a certain amount of energy. And if it's a very complicated or very strong vibration, I may need more energy. So for the step from here to here is a bigger step, So that means that I need more energy to excite that vibrational state. And if I heat up a gas, what will be the first vibrational states that will be occupied by the molecule? The easiest one to excite. Lowest ones, yes. So if you would look at a molecule at a certain temperature, you can draw a graph of how likely one of the vibration states, how likely it is that the molecule is in a certain vibration state. And the bigger the energy step that you need, the smaller the probability. Now, you have basically all the tools to understand now why the intensity of this line and these two lines is so much weaker than the one that's very close to this gradient length. Due to temperature, the small energy steps, the lower vibrational states are occupied. You need more and more energy, or you need the higher and higher temperature of the gas to excite the higher vibrational states of the molecule. So, what can you deduce from this measurement now? Very sophisticated thing to do.
Almost all of them are occupied.
Oh, not really. They contribute. I wouldn't say they're fully occupied, but what does it tell? Let's say I do two measurements, one at the very low temperature of the gas and one at the very high temperature of the gas. How do you think this part of the spectrum will change? Let's start with the very low temperature of the gas. Is it likely then that this state will be occupied? No, okay, but that one here is, yeah, moderately probable. Okay, let's say it has a, let's put a number on it, there's a probability of 20% for this vibrational state to be occupied. They go to the next ones, higher in energy. What is the probability of this one? Will it be higher or lower than 10%?
Lower.
Lower, exactly, lower. And then at this state, it will be lower than that. So this graph tells you the excitation levels of the molecule due to temperature. If I now go to a gas at a very high temperature, this has a probability of, let's say, 90% to be occupied. But then this one also has a very high probability on the order of 90. On the way out here, will the probability drop again. And basically that's given by Boltzmann's constant. But the point is that by measuring the spectrum, you can deduce the temperature of the gas. Okay, when I come to a later part of the spectrum, my talk, I'll talk about cars. And that was a technique that was invented at General Motors. And why did they investigate Raman scattering? They were interested in the temperature in the combustion chamber. So they used this Raman effect to determine what the temperature was inside their cylinders. Okay. So, evolution of Raman spectroscopy. The other thing I forgot to mention, but let's take a look at this this graph again. That is not so visible, but you can see that the Rayleigh scattering, the light that's emitted at the same wavelength, is extremely strong compared to the other intensities of these lines here. So the Raman effect is very weak. And you can send in about 1 million photons, and then maybe one of these million photons is converted to a wavelength of a longer or shorter wavelength. So then there goes Raman scattering. It's a very, it's a process with a very low probability. And so to study this, you need light with a high intensity, and you need light of a very narrow single wavelength. And at that time, before the 60s, you had to do with mercury lamps and sunlight. So not really powerful sources to study this effect. But then in the 60s, the lasers were invented that allowed you to produce, like this one here, very nice collimated monochromatic beam of light that you could create at very high intensities. The lasers were needed to further study this Raman effect. Then in the mid-80s, techniques came up like Fourier transform spectroscopy. That's a method of measuring a spectrum in a very sensitive way. So you're not using a spectrometer anymore, but you use basically a fabric probe cavity that you can tune to very carefully measure the transmission and thereby determine wavelength. Then charge coupled devices. Well, you're all familiar with it. They're in your phones. Very sensitive detectors, quantum efficiencies on the approaching 1, which means that nearly every photon is converted into an electron in the chip that you can detect. What was needed, I will get to that, is holographic filters, computers, and then near infrared lasers. And most lasers are intended to be visible, and slowly it was progress towards near and far infrared. And then with all these advantages in the 1990s, Raman became popular in biomedical applications. So all these advances are needed in order to measure something in biological tissue. So if you look at if you look at the vibrational states of a molecule, in how many ways can a molecule vibrate? Well, it depends on the number of atoms. So in principle, a molecule with n atoms can have 3 n minus 6 different vibrational levels. And there's one exception, that is for a linear molecule, let's say a chain, that has 3 n minus 5 different molecular vibration levels. The interesting thing is that the vibrations of the molecule are very molecule specific. So you can take one molecule, you can take another molecule, and the vibrational levels will be different. The energy that is needed to excite the vibrational state of the molecule is different. So, and this makes the Raman spectroscopy very interesting because it allows you to identify the molecule from the spectrum it emits. And we call that basically the fingerprint of a molecule. So the spectra, Raman spectra, are very different for different molecules. And as I explained already in the beginning, it can tell you something about the environment the molecule is in. So the example that I gave you is that you can determine the temperature of the environment of the molecule. But there are other things, what crystal form is the molecule, redox state, and so on. So it can also tell you something about the environment of the molecule. And so there are two important techniques to record these vibrational spectra. One is infrared absorption spectroscopy. And this is the technique where you basically try to excite directly the vibrational level of the molecule. These molecules, the vibrational states are at very low energy, so that means you have to excite it in the far infrared, so low energy photons, where you directly excite the vibration of the molecule. And the other method is Raman spectroscopy. That's the technique that I described so far, where you have an incoming light beam that is scattered off the molecule and you get energy transferred to it or from the scattered beam. So infrared absorption spectroscopy, direct absorption of the energy by the molecule. Raman spectroscopy, a scattering process where the light that is scattered has a higher or lower energy. So if you go then to these two different mechanisms, IR absorption and Raman active vibrations, we first go back to the most important scattering process, elastic scattering and radial scattering. Then we get the inelastic scattering, that's a nuclear motion induced, so there's energy transfer from or to the photon. Inelastic and vibration levels of the molecule are involved. Then we have vibrations that cause a change in the dipole of the molecule. And these vibrations are infrared active, which means that they can directly absorb infrared radiation. And vibration is the change that causes a change in the polarizability of the electron cloud around the molecule are Raman activity. So I will get to that, what the difference is between a change in the dipole or the change in the polarizability. Let's do this a little bit. So a change in the dipole of the molecule means if you have a natural molecule, in general, there is one atom that has that needs one electron, and the other atom has an electron, a single electron in its outer shell. And why do they like to combine? Because then they share that one electron. The one that lacks one borrows the electron from the other atom, and the other atom now has a nicely full all outer shells. Okay, so that's creating the bond. But the fact that there is a transfer of the electron from one atom to the other atom means that there is a charge imbalance now, because the nucleus of the atom holds the same charge. So the molecule has a charge distribution. It is charged. You can say it has a dipole. There's an electric field in the molecule. Let's say you have a transfer of that one electron to the other atom, then this atom becomes more negative, this atom becomes more positive, so you get an electric field over the molecule. So that is a molecule that has a dipole. Vibrations that have created change in polarizability. Let me explain what polarizability is. Polarizability is the ability to distort the electron cloud around the atom. So if you can polarize the molecule, it means you can induce that dipole effect. You can move the electrons from, let's say, you can move the electrons from one atom to the other atom by your electromagnetic radiation. And the easier it is to transfer with your electromagnetic field the electrons from one side to the other, that indicates that the molecule is more polarizable. Two different effects. So if you then look at these vibrational levels to give you an idea of in what energy range are they. So they are in units that I will get to, that is 3,600 inverse centimeter to about 400 inverse centimeter. And if you convert it to wavelength, that corresponds to wavelength about 2.8 micron to 12 micron. And so this is the far infrared radiation, that is the part of the spectrum that is basically radiated out by warm bodies. So if you take your own body temperature, like 37 degrees centigrade, you will radiate energy within this window, thermal energy. Okay, and then what I will, that is in the next slide, I will show you a simple molecule, CO2, 3 atoms, and I'll show you the asymmetric stretch, which will be infrared active, so it has a dipole moment, and I will show you the symmetric stretch, and that one is Raman active. Any questions about it? I mean, I realized that a dipole of a moment and of a molecule and the polarizability of a molecule are most easy concepts. Any questions about it? I'm more than willing to spend a little more time on that. If not, then I'll continue, and maybe after the next slide you have more questions.
Can you please repeat the definition of polarizability?
Polarizability, you should see, so you polarize the molecule, which means that you create a charge difference between atom 1 and atom 2. So you generate then an electric field over the molecule. The polarizability tells you how easy it is to do that. So if, let's say, the electrons are tightly bound around their atoms, it's very difficult to move that electron a little bit to the other side and to create a dipole moment in the molecule. But if the electron is very loosely bound to the molecule and it orbits at a large distance from it, it's easier to move that electron to one side of the molecule, and that means it's more polarizable. you have to realize when they say move, this is on the time scale of the frequency of light. So it means that you rapidly try and move these electrons back and forth, or this electron cloud basically around the molecule from left to right based on the electromagnetic field that is incident on it. Okay, so we have these vibrations. Let's look at this one. So it's a 3-atom molecule, CO2. So the carbon is in the center, the oxygens are on the outside. And if you look at this vibration, what kind of vibration do I look at? I am the carbon. These are the oxygens. What do they do? But how? Like this? Like this, very good. This is the vibration of the molecule, okay? And then you look at this one, what kind of vibration is that? Different vibration. And then the third one is, yeah, I do it like this. I basically like this. It's bending. So it's not vibrating on a line, but it's a bending vibration.
So it's not symmetrical like in the picture.
Sorry?
So it's not symmetrical.
What do you mean it's not symmetrical?
It's symmetrical, just depending on the axis.
Help me out.
I was wondering if it's also symmetrical, but you don't call it symmetrical vibration. You call it symmetrical.
Yeah, it is labeled asymmetric. This is asymmetric.
I mean the third one, the bending.
Yes. Let's look now at the induced electric field in the molecule. So you have to help me out. I think for CO2, the carbon has sharing the electrons with the oxygen, right? Anyway, so they move out like this. Does that change the dipole moment of the molecule? You said no. Very well. Why? It's a good answer. Why? It's not easy to interpret, but you could say that if there is a charge imbalance, it will not change when you do this vibration. Especially if let's compare to the second one. Here we have that carbon in the center that basically moves to one side and then to the other side. And let's assume now the carbon is more or less positively charged because it's sharing its electrons with the oxygen. Then I should be careful here. But you can imagine that if this carbon is slightly positively charged, that moving it to one side will create a dipole in the molecule. There will be now an electric field directed in this direction, the direction that you see here. So the point here is that by having that carbon move back and forth, you create a changing charge distribution of the molecule. And the carbon is at this side, we have a field pointing in this direction. When the carbon is in this position, you have an electrical field pointing in the other direction.
And how do you know the direction of the field?
That depends on the charge distribution inside the molecule. So it's, does it need an electron from the others, or does it share out its electrons with the atoms around it? And then I think this is also a fairly obvious picture then on that charge distribution. Again, here if you have the carbon move up and the oxygens are down here, the oxygens are slightly negatively charged, the carbon is slightly positively charged, you get also an electric field of the molecule. So the message here is that due to the vibration, you get a change in the dipole moment of the molecule, especially for this one. This is here you can see there's a dipole moment. Here's the dipole moment pointing up. Here's the dipole moment pointing down. In this case, the dipole moment pointing left, and here it's pointing right. So these two vibrations create a dipole moment in the molecule. I mentioned two effects: a dipole in the molecule and the polarizability. So let's now look at this one, the polarizability. The polarizability was the capability of bringing the electron cloud into motion. If we look at this molecule, we can imagine that if my two oxygens move out and the whole molecule becomes a little bigger, that the electrons around it also become more loosely bound to the whole molecule. And because they become more loosely bound, it's easier to move them. The electric field, electric field of the light that falls onto the molecule is now better capable of inducing a motion in this molecule. And when it induces a motion in that electron cloud around the molecule, it creates a dipole moment. So now the dipole moment is created by the incident light and not by the internal vibration of the molecule itself. Okay, so this vibration creates a change in the polarizability of the molecule, and these two vibrations create a change in the dipole moment of the molecule. And then what is the consequence of that? The consequence is that this vibration is Raman active, creates Raman scattering, and these two vibrations are IR active. So these two vibration states can be excited directly by low energy light, infrared radiation, and this one will only show it as a Raman. So what does it mean if I investigate this molecule by a laser that does not excite at these resonant frequencies of these vibrations? I will only see this line here. I can only draw this vibration of the molecule. There's an important distinction between IR active and infrared active, what you can see in the molecule. All right, was that clear? It's important. This is the fundamental of this technique. Yes?
Can you explain one more time why the polarizability of the symmetric one is not?
This one.
Yeah.
So it is the capability to move the electron cloud around the molecule. The easier it is to move the electrons, the higher polarizability. What do you need in order to move these electrons easily? You want them to be more loosely bound to the molecule. So let's say the closer the electrons are orbiting the molecule, the tighter they're bound. But if they're further away, the attraction of these positive nuclei, the force is becoming less, and so it's more easy to influence their motions.
And that's with symmetrical because that's like the ideal position compared to like the asymmetrical one. You have like that one is like further away. Is that right?
What I'm trying to say is because the size of the molecule is changing, it's breathing. And so when it oscillates out, the whole molecule becomes bigger. You can interpret that as also that the electron cloud that's around it is affected by the whole, basically the increase in size of the molecule, which makes it then, as a consequence, easier to move the electrons by an electromagnetic field. More questions? Yes.
What's this graph of the x-axis graph?
You mean the lower one?
Yeah, both.
These two graphs. Oh, on the horizontal axis, you mean this axis here?
Yeah.
That is inverse centimeters. And I will show you later that that is an energy scale. So it corresponds to energy. This is the higher this number, the larger the energy in the vibration. Oh, that's one nice. There's one the only exercise that I have is calculating the wavelength to inverse wavelength. So you know how it works. But it's so in other words, it's an energy axis. All right, I think it's time for a break. Do I do something with the recording or do I leave it alone? What, sorry? Oh, ik heb Ja, dat is Okay, so look there now. Shall we resume? Okay, so what I would like to do is give you a classical derivation of the Raman. Okay, so what I need is I I need an incident electric field. This is my incident electric field. It has an amplitude and a cosine of 2 pi times the frequency of that light times t. So this describes my oscillating electrical incident field. And also I want to describe the induced molecular electrical dipole. So this dipole in a molecule is a consequence of this external field. And so P is the electric dipole of the molecule, and it's proportional to alpha times the incident electrical field. And alpha now is that polarizability, the ease with which you can distort the electrons from the molecule and induce this dipole moment. So the dipole moment of the molecule is proportional to the polarizability. Now let's take a look at that polarizability of the molecule. Let's say in its resting state, it has a certain polarizability, a certain ease with which you can distort the electron current. But if we now start to move one of the molecules away, and let's say we change the bond length between two atoms, that induces a change in this polarizability. It will be easier or harder to move these electrons. So I express that polarizability of the molecule as the resting state polarizability plus the change in the polarizability due to the motion, the distance between the atoms, the bond length. And I denote that by Q. Q is this distance between two atoms. And then the bond length change times the change of the polarizability with the length change gives me this polarizability. So these are all the things that I need, because I can say now that that bond length oscillates at the frequency of mu r, where mu r is the Raman vibration level of the molecule or the internal vibration of the molecule. So Q, bond length, changes with this, oscillates with this frequency here. And if I insert this Q now back into my expression for the polarizability, then the polarizability becomes the resting state plus the alpha dr times Q naught cosinus 2 pi mu r times t. So this is how the polarizability changes as a consequence of the internal vibration of the molecule. Okay. So now I go back to the polarizability of the molecule. Polarizability of the molecule was given by alpha times the incident field, my electromagnetic radiation. So my polarizability, my dipole moment becomes now alpha naught times my incoming field. This is my incoming field, E0 cosine 2 pi mu I t, plus this term. And this term is the product of my incident field and this vibration of the molecule. And so this term is given originally by the E naught cosine 2 pi mu I t times alpha dr Q naught cosine 2 pi mu r. And what I see here, I see a product of two cosines. And a product of two cosines I can write as half times the sum of the frequency, so that would be the cosine of 2 pi mu I plus mu r c plus cosine of 2 pi mu I minus mu r t. Okay, so product of two cosines, yes.
Can you raise the board, please?
product of two cosines you can write as the sum of the two frequencies and the difference of the two frequencies. And what you see now, that this dipole starts to oscillate at three frequencies. One is my incident frequency, which I can say now is my Rayleigh scattering, my elastic scattering. One term where the dipole oscillates at a higher frequency, incident plus frequency of the vibration of the molecule, and one incident light minus the frequency of the vibration of the molecule. And so this dipole represents an electric field over the molecule. And this electric field oscillates. So it radiates. It's this dipole, this oscillating dipole, that generates radiation now at my original frequency Rayleigh scattering, at my anti-Stokes frequency, the higher one, and at my lower frequency, the Stokes scattering. So with this very simple derivation, I've shown you that I generate now these anti-Stokes frequencies and Stokes frequencies. If you look at those molecular vibrations, it has a strange lagging effect. So the frequency with which a molecule oscillates, you can estimate by this expression here. It's the square root of k, which is a kind of string constant, multiplied by the sum of the two masses divided by the product of the two masses. It's then the frequency in hertz. A very nice way to look at these scattering effects is with the Jablonski diagram. And it's very nice because it allows us to look at more complicated things that can happen when you have scattering, let's say, in tissue. So the way you express it is in energy levels. So the vertical state here, the vertical axis is here energy. And what I've depicted here is the lower electron band. So let's say an electron orbiting in the ground state around the molecule. And then these different energy levels represent different vibrational energies of the molecule. And this is then an electron in a higher excited state, and with that also you can the energy of the molecule is split because of the different vibrational energies that the molecule can have. So the Jablonski diagram shows you an energy diagram of a molecule. And we can visualize now this Raman process by saying, okay, I start in the ground state. It's the energy of my photon that excites me to a non-existent or virtual state here. And from this virtual state, I decay down to this level here, the first vibrational level of the molecule. So this is the Jablonski diagram then of a laser incident on a molecule, exciting a vibrational state and emitting a photon at the lower energy because this arrow is shorter on this energy axis. So the Jablonski diagram, in this case, you excite the molecule with into a virtual state that doesn't exist, and then it decays down to this first vibrational level. Like I said, we all know about electronic states of molecules, but now these electronic states of molecules are coupled to the vibrational levels of the molecule. So we get a split in the energy levels. We have a ground state of a molecule, electronic ground state, but then we have the vibrational levels that split up this ground state in different energy levels. Same holds for the higher orbiting electrons. They split up also due to the internal vibrations of the molecule. So this is the picture of the energy states the molecule can be in, based on electronic excitation and vibrational levels of the molecule. Okay, or based on the formula I showed you before, if you have lighter atoms, they you have the faster vibrations, so they contain more energy. And if you have heavier atoms, you have lower vibrations, so slower vibrations, so lower energy. So the excited state of the molecule depends on the masses of the atoms in the molecule. And this is then an example of a cholesterol molecule that contains many, many molecules, many different vibrational levels. And this is then an example of such a Raman spectrum. And you see here peaks that correspond to certain vibrational states of the molecule. So the CC stretch, that is the two carbons in the chain that oscillate like this. That's a stretch vibration. You have the CH2 and CH3, like here and here, and they can be bending vibration where the whole structure kind of bends around the backbone. And so on, all different kinds of vibrations, all different energy levels, producing a Raman spectrum like this. So to help you out, again, this is a horizontal axis shown here in inverse centimeters, and I will shortly show you the inverse centimeters actually is an energy axis. So the larger this number, the higher the energy of the vibrational level. And you can see it's a pretty fine structure. It has lots of features, and that makes it very nice to identify a molecule. This is the reason why we say that Raman scattering provides a fingerprint of the molecule. But for each molecule, for different molecules, these spectra will be different. So it allows you to identify the molecule that you're looking at by this effect. That's the true power of Raman scattering. Fingerprints, yes. Okay, then the energy axis. So we can describe the energy of a photon by Planck's constant times the velocity divided by the wavelength. That also means that there's a way of expressing the difference in energy between the incident photon and the emitted photon. So the energy of the incident photon is hc multiplied by 1 over the initial wavelength, minus the energy of the emitted photon times minus 1 over the final wavelength. So when you look at this unit here, this is a unit inverse meters. And then the convenient way we express that is we don't express it as inverse meters, but as inverse centimeters. Okay. So now you see that this unit inverse centimeters is an energy axis. And then this is the exercise that you can make now actually. So you have 15 minutes to try to figure this out. I have a near infrared excitation at 830 nanometers, and that is 12,048 inverse centimeters. So first try and make that conversion. Then I say the typical Raman shift is about 1,000 inverse centimeters. And why did I choose 1,000? Well, let's take a look at this. The spectrum of this cholesterol molecule, we see that it's basically between 600 and 1800 inverse centimeters, so 1,000 centimeters about right here. If I would illuminate this molecule and I see the light coming off, how much will it have shifted in wavelength? So let's assume that 1,000 inverse centimeters. So the question is, what is the wavelength that is emitted if the Raman shift is 1,000 inverse centimeters? And I think the trickiest part is it's easy to calculate this in inverse meters. There's 1 over lambda in it, but you have to convert it not to inverse meters, but to inverse centimeters. So if I start with 830 nanometers and I do 1 over lambda, what is my answer? Anybody want to give an answer? Yeah, I know, but I want you to show it to me. So what is 1 over lambda? Well, I do 1 divided by 830 nanometers. What do I get? And let's stick to the unit meters for a moment, because that's an SI unit. And this makes it easier to what the answer that I wanted. What is the answer now? So that's 1,209,890 per meter, or meter minus 1. In other words, you could say this is the number of wavelengths that fits into 1 meter. But my unit should be per centimeters. So if this is the number of wavelengths that fit into a meter, the number of wavelengths that fit into a centimeter will be smaller. By how much? A factor of 100. Thank you. So now it becomes 12, 0, 4, 8 per centimeter or centimeter minus 1. Okay, so now we have got our unit centimeter per centimeter. And now the Raman shift. This is a 34R. What will be the radiation, the Raman shifted radiation expressed in inverse centimeters? And start, the original photo is 12,048 inverse centimeter. What will be the wavelength of the emitted light? Sorry, wavelength. Let's start with expressing in inverse centimeters.
Say again, sorry.
What is the energy of the photon, or the wavelength of the photon expressed in inverse centimeters? That's and we have a Raman shift of 1,000 centimeters, inverse centimeters. And I'm looking for the Stokes shifted photon. Any idea? Front row? No? So original wavelength in inverse centimeters. The new wavelength will be 11048 inverse centimeters. I have a shift of 1,000. And this new number is lower, right? And remember, this is an energy axis. So this photon has a higher energy than this photon in this inverse centimeter scale. Okay, so this is now my wavelength in inverse centimeters. What is it in inverse meters? Here, per meter to per centimeter, I divide it by 100. Now I go back from my centimeters to meters. What is it? Yeah, it's so it's 1.1048 per meter, which is equal to 1 over the wavelength of my Raman emitted light. And what is this now in wavelength? What is R? What is lambda R now? Second row. Sorry?
905.
Yeah, 905. So this is the 905 nanometers. Expect you to be able to do this on an exam. Huh? So what you see, you come in with a wavelength of 830 nanometers, and the light that is emitted is now 905, shifted down. Homework is calculated for the anti-Stokes photon. Plus. Okay. Second calculation. Okay, I cannot clearly see the derivation. What do I do? Can I change this camera? Is it okay? Dear, can you check if it's now better visible? Okay, the second question is the following. If you look now at this emission spectrum, you see that these lines have a certain width. Let's say this line here, it has a certain width. And now the question is, how wide is this line if you express it in nanometers? And what I'm telling you is the width of this line is 10 inverse centimeters. And so we have our shift, 1,000 inverse centimeters, that is the shift. The width of this peak is 10 inverse centimeters. How wide is that in wavelength? And the reason for this exercise is I want to give you a feel for the kind of resolution in your spectrometer that you need to see this. And I want to, and let's already do that, but let's compare this to fluorescence of tissue. I think that here, if you explain fluorescence and how broad then fluorescence of tissue can have a width of tens or hundreds of nanometer wide. It's a very slowly changing function as a function of wavelength. And the point I want to make is that when you look at Raman, these peaks are very narrow. And that makes it so nice to identify these different molecules. And it's a very narrow, very specific spectrum that you're looking at. And so for you to get the feel of the width of these lines, how wide is such a peak, then I would like you to calculate the difference in wavelength, delta lambda R, for this for a line width of 10 inverse centimeter, which is a really realistic number for a molecule. Yes.
Why is the line width expressed in nanometers?
No, I want it expressed in nanometers. It's expressed in inverse centimeters, which is a nice energy scale, right? But do you know? Can you tell me what the wavelength is? No. I mean, in this, that's why well maybe we did the calculation already. But here I showed you the spectrum expressed in inverse centimeters. But the way I measure it is with a spectrometer, where I measure it in wavelength. And then when I have my wavelength, I need to convert it, knowing my instant wavelength and detected wavelength, into this energy axis for a Raman diagram, for a Raman scattering plot. If you, so just to get an idea how wide if this is 10 inverse centimeters in wavelength, what is that in wavelength when you measure it? I mean, I can tell you if it's 1 millionth of a nanometer, it won't be able to measure it. There's no spectrometer sensitive. Sorry? Measure resolution of the spectrometer is. So anybody, how would you approach this problem?
So you still have the same exciting, the exciting wavelength, right? So
Yeah, let's go back to the exercise.
the inverted centimeters, so 12,048.
This one remains the same. Typical Raman shift is 1,000. If the line width is 10 nanometer, 10 inverse centimeters, what is this Raman shift then? If this is my peak, from here to here,
It's like 12,048, and then one divided by that as the initial, and then minus 1 divided by 12,038, right? Because the minus is there.
I'm not very good in a verbal derivation.
No, if you use like the 12,048 minus 10,
Minus 10.
yeah, or the 12,038, and then
A difference.
yeah.
Oh,
The difference 10, so you have eventually 0.79.
you mean you want to subtract it from this one?
Yeah, well, from the 12,000.
Well, I'm not sure if that works. So you want to just subtract the 10 from this one,
Yeah.
and then
Well, that's how you know the difference, right? So you have 12,048, that's like the right side, and you have 12,038 on the left side.
I see where you're going, and that's a very quick, rough estimate, but it can be more precise. But it's not. I wouldn't say it's completely wrong. You can indeed subtract the 10 inverse centimeter from this number, convert it back to a wavelength, and look how much this wavelength is different from your 830.
Yeah.
But it doesn't really work that way nearly. It's approximation. But what I really would like to do is take this incident wavelength and not subtract 1,000 from it, which is my shift, but I'll subtract 9,905, 995 from it. And that, so this peak is my 1,000 centimeter minus 1. This point is my 995, and this point is my 1005 inverse centimeter. And then I want to know this bit. And that's not completely equal, although so that basically gave you the answer already. What you need to do is you take this incident wavelength, you subtract 995 from it, doing the exact same calculation to get to a certain wavelength. You do the same, but now you subtract 1,005. You again get a new wavelength, and then the delta lambda that I'm looking for is the wavelength difference between the two. Any result? Yeah, I'm not moving. Anybody has an answer? You have an answer. Oh, and that's with your simple calculation, right?
And now it's open data for calculation.
Okay, you see there's a difference.
Yeah.
And the correct answer is indeed 0.8. So if you do it properly, then you have a shift of 11,053 inverse centimeters. And the other one is 11,043 inverse centimeters. Corresponds to this wavelength in nanometers. And then the difference is about 0.8 nanometers. So you can see that that wavelength shift is very small, a fraction of a nanometer. And this peak here, if you translate this peak, let's have this peak here, that's 10 inverse centimeters in width, then that is when I use a spectrometer to measure it, it's only 0.8 nanometers. All right, I think that brings me to a break. Let's do a break. Well, this is where we'll continue. Weird, there are all kinds of chat messages, but I found all yeah. Yeah. Ja, maar dat is dus dat is de truc als je rekent met die 1 over.
Ja. Nee, die truc die zitten wel in. Ja, maar dat ging dat van een oude rekening van de rekening. Maar dat was van het eerste stukje.
Ja. Het is wel zo dat als je dat moet afschaffen.
Ja.
Tweede orde.
Noem ik dat.
Ja, precies.
Ik kan niet goed uitleggen hoe het is. Kijk, die 830 is een korte golf. Als je daar ziet, dat als je 830 groot als je dat mee voor 5,
Ja.
en dat maakt dus niet dat ene voorwijs. En in deze maak je iets groter. Goed zo.
Dan weet je dat het niet duidelijk is back. Motivate. Keep learning. Ik zag net Japanse tekens. De wacht is van. Hij ook niet man. Hij ook is het nu? Zou dit zo
Ja, bij heel Koreaans.
Mungkin dat is ook. Dit is
Okay, we'll be further. I'd like to continue. Okay, let's look at a little bit more at the Jablonski diagrams because they're very insightful in understanding the effects that are going on. Okay, so again, Jablonski diagram, the vertical axis is energy, and what you can see here are energy differences in different quantum states of the molecule. So here we have the ground state, electronic ground state, so electrons are all in their nearest shells, and we get the split up of this ground state due to the internal vibrations of the molecule. And what is then what happens when you shine a laser on it? Well, you excite it to a virtual level, and from the virtual level, you fall down back to the ground state. You immediately see in this energy diagram that that emitted photon is the same wavelength of the original photon. So this is basically a Jablonski diagram of elastic scattering. The other effect that can happen is that from this virtual state here, it drops down to the first excited state of the vibration of the molecule, or the second vibration state of the molecule, or the third vibration state of the molecule. And if you know the energy states of the molecule, then you can calculate what the wavelengths are that will be emitted due to this Raman process. Okay, energy diagram for Raman scattering. We can also look at the anti-Stokes scattering, where we emit a photon of a longer wavelength. Sorry, of a higher energy, shorter wavelength. So first, we are already in the excited state, also on the third row, still excited. So we are already in a vibrational excited state. We couple to a virtual level, and we fall down to that same vibration level. Elastic scattering, photon of the same energy. But we can also fall down to the vibrational ground state of the molecule. In the Jablonski diagram, this arrow is longer, denoting a larger energy difference, so a shorter wavelength is emitted. And this can happen for all these different vibrational levels that are occupied in the molecule. So if the third vibrational level is occupied, it goes in this virtual state and drop down to the ground state, you can see that the wavelength emitted is even shorter. You will see later why these Jablonski diagrams are so useful, because you can also include now fluorescence and resonance and so on. So that I alluded already to it, that the anti-Stokes is due to vibrational levels that are occupied due to thermal excitation. So this is an Raman spectrum of sulfur at room temperature. You can see here this line at 0 is Rayleigh scattering, and then you get these 3 Stokes shifted lines. And then you can see that if you look at the anti-Stokes, that we can see at least the first 2 here. These 2 lines, vibration levels, are mirrored on the other side. And they have the same energy difference. So from here to this line here is about 170 per centimeters. That's also where this peak occurs. And the same also this peak, let's say 210 or 220. And here indeed the peak is 210 to 20. So the Stokes spectrum and the anti-Stokes spectrum are basically mirrored, but the intensity depends on whether or not a molecule is in this higher vibrational state. And to determine that, we use Boltzmann's equation. So the occupancy of level 1 and 1 divided by the ground state is proportional to e to the power delta energy divided by kT. This is the thermal occupation of these vibrational levels. And as a rule of thumb, kT is about 200 inverse centimeters. So at room temperature. So at room temperature, you can expect the excited state N1 to be occupied. And you can see that here, that 170 and 210 inverse centimeters are indeed vibrationally excited thermal by the heat, But if you look at this line here around, what is it, 480 or something, it becomes very weak in the anti-Stokes shifted because it's barely thermally excited. This is what I'm basically, I started the lecture with that this is also a means to determine the temperature of a gas. Okay, now some probabilities, rough numbers. Huh? So if you take near IR light in tissue, then we have mu s prime of about 1 millimeter. That is the length, the distance that infrared light travels before the direction is completely scrambled. Or you can always also express this as mean free path. Near infrared absorption is about 10 centimeters. So the average distance that a photon will travel is about 10 centimeters. If you look at red absorption in water, then it's about 5 meters. So red light travels much further than infrared light. The infrared absorption of infrared light is much higher. But if you then look at this Raman scattering in tissue, the distance that the photon needs to travel before it generates a Raman photon is about 3 kilometers. That is, in a way, you can express this as a cross section. What is the cross section of the molecule for scattering is, well, I can't say it's a millimeter, but it's a certain area. And then if I look at the cross section for the Raman effect, it's about 1,000,000 times smaller than for scattering. So the Raman effect has a really low probability. It's much weaker. That makes it problematic. So how inefficient? Oh, I have here cross section. It's 10 to the power minus 30 square centimeters of cross section for Raman scattering. So about 1 in 100 million photons is Raman scattered. So that was a problem. The Raman effect does not have a large probability. The signals are weak. You need long exposure times and a high concentration of the built material. The invention of the laser has changed it because at least one knob you could turn on was the intensity of the incident light. And the applications are very wide: chemical analysis, geology, forensics, customs. If you want to know if something's a forgery, you can also use Raman spectroscopy to determine the elements. Because in the past they used certain versions of lead or egg white, or I don't know, and the forger can't really reproduce those elements perfectly, and so it shows up as something that's not from that time. Contemporary means it's a fraud. Raman intensity, I'm giving you some formula. So the intensity of the radiation, the Raman scattered light, is proportional to the intensity, the polarizability squared, and the wavelength to the 4th power. So this is an important thing because it means that if you use shorter wavelength light, let's say you could use 1,000 nanometer, or you could use 500 nanometer as your incident laser. The Raman shift in inverse centimeters will be the same, but it goes with the frequency to the 4th power. So 500 nanometer is 2 to the power 4 times, generates 2 to the power 4 times more photons. The polarizability of the molecule is something that you can influence by resonant Raman scattering. And I will show you in the Dipole diagram later what that means. Despite this advantage of shorter wavelength, the wavelengths that are used in Raman scattering, especially in biomedical optics, are long, and I will explain you why. Why do we not choose these really short wavelengths? So this is conventional Raman, incident photon, Raman shifted, Stokes shifted photons. Because you can also make use of higher electronic states. Because what we did here is we couple into what we call a virtual state, or a vacuum state, or a state that doesn't really exist. So it's very difficult to excite something that doesn't really exist. But if you excite to an existing electronic level, this probability is already a lot higher. So you make use of a resonance effect that this transition is much more likely to also generate the photons that fall down. So resonant Raman scattering, and it provides a significant enhancement of your Raman signal. But let's take a look at fluorescence. So fluorescence is the effect that you shine light on a tissue and then you excite electronic states in the material. You get internal decay, and then at some point the photon falls down again to the ground state, emitting a photon, a fluorescent photon. Fluorescent photon is completely different from a Raman photon, where you go to internal vibrations. The fluorescent photon is a photon where you excite a molecule into a higher electronic state. You get some decay in these higher electronic states, and then you fall down from that higher electronic state back to the ground state. This is, in inverse centimeter, the fluorescent spectrum. And what you see is it contains many peaks, but also a very strong background in that area of interest. In the 600 to 1800 inverse centimeters, that was the region of interest where you had your fingerprint region, where all these molecules have their Raman shapes. But here you can see that there's also a huge fluorescent background, and this is for an excitation of 630 nanometers. So the Raman effect has to compete with fluorescence, and the problem is in general that fluorescence is much more likely to happen than Raman. So your Raman spectrum will be completely overwhelmed by fluorescence. And so what is that in a Jablonski diagram? This is the Jablonski diagram of Raman scattering and fluorescence. So what we see here is the incident light coupling to a vibrational state and then falling down into the ground state. But since there is an electronic state there, and so this is the resonant Raman, you can also excite this one. You get internal decay into the ground state of this higher electronic state, and then it decay down into the ground state. And that photon, this photon, has a similar wavelength as the Raman scattered photon. So here you get you're completely overwhelmed by your fluorescent spectrum. One trick is to go to UV resonant scattering. So you use a really short excitation wavelength. You skip one electronic band, you go to a higher one, and from there you fall down into the vibrational first excited level. And you send out a photon of a fairly short wavelength. Fluorescence in this case would be, if you excite to this state, you get non-radiated decay into this S1 excited state, and from there you fall down into the ground state. And you immediately see that this photon has a completely different wavelength from the Raman scattered photon. So here you can suppress the fluorescent background by wavelength filtering. Your Raman photon has a much shorter wavelength than what happens here. So this is UV resonant excitation. This is excitation in invisible. In invisible, you have a lot of molecules that fluoresce. And then we go to the near IR excitation. And in that case, the incident photon doesn't have enough energy to excite to your first electronic state. So this process doesn't happen. You couple somewhere to this virtual state, and from this virtual state, you drop down into the ground state. So the key here is that you can eliminate the fluorescent background by using a wavelength that is so long that you do not excite electronic states, and you can, in that way, suppress your fluorescence. And for tissue optics, that's really important. So near IR excitation, wavelength longer than 700 nanometers. The problem remains that it is a very weak process. 1 in 100 million probability. Let me see what's next. So, brief summary of advantages. It's broad applicable. Most materials have molecular vibrations. It's possible to measure it in situ, which means from a distance. You don't need contact with the material. It's used with light. You can do molecular identification because of this fingerprint feature of Raman spectrum of the molecule. There is very little to no sample preparation needed, and you have very little interference from the presence of water, except for the absorption. Like I said, Raman spectra are molecule specific. It has sharp features, and these are, for instance, the 3 spectra of glucose, lactic acid, and creatinine. And you can see that they're completely different. So this would allow you to do a non-contact analysis of blood, for instance, on these glucose levels, lactic acid, and creatinine. Okay, now if you want to move to biomedical optics, you want to measure in tissue, you need endoscopes, you need your sources in proximity of the tissue. So in general, we use fiber optics. And that immediately poses a problem because the fiber itself already generates a Raman signal. And so, and then the disadvantage is you go through your fiber, let's say the fiber is 3 meters to get to the patient. Then it travels through tissue, about 1 millimeter, and then it travels back again 3 meters through your fiber. So the interaction length in the fiber is much, much larger than in the tissue. And so even if the Raman effect in the fiber is weaker than in the tissue, because you propagate such a long length, about, what is it, 3,000 times longer, still it generates a background. So the background in fibers is really a difficult issue. It's not only true, by the way, for Raman scattering. This Raman effect in fibers is also a problem if you just want to measure fluorescence in tissue. Now, let's say you come in with a certain wavelength on your tissue, you want to measure the fluorescence spectrum. Unfortunately, you have a strong Raman background from the fiber itself. Then you would think, well, I can just subtract it. Does that work? I have 1 million IR photons background from the fiber, and I have 100 Raman photons. Can I determine these 100 Raman photons? Can I just take the 1,100,000 photons and I subtract 1 million and I am left with 100 photons and I've done a perfect background subtraction? Who's for this plan? Who likes this? Like this, you can do this. Nobody. Wow, that's a great solution, isn't it? Take my 1,100 photons. I subtract my background with 1 million and end up with the 100 photons I want to measure. Okay, let's do that. We're not. Who has an idea why it might not work?
How are you going to figure out, or like, how are you going to distinguish them?
Well, you take your fiber and before you stick it into the tissue, you measure the amount of signal that you get back, and you know that's your fiber. You stick it, and that's 1 million. You stick it into the tissue, you measure 1,100,000. You subtract 1 million. That's your signal. Why doesn't this work? When you measure 1 million photons, what do you think the variance is? When I have on average 1 million photons, what is the deviation from that 1 million? In the back, nobody.
I would say large.
It's large. That's a good guess. Because it's really poking you in that direction. But yes, it's large. Do you know how large?
No, I mean, for 1 million, probably incredibly large.
Sorry?
For 1 million photons, probably incredibly large. I mean, I thought we were presuming that we actually know it's.
Yeah, but how do you know it's a million? That's because you do that measurement that you average over time, let's say for a minute, and then you know what your average number of photons per second will be. Let me, the answer is right here on the sheet, the bottom, the last sentence, shot noise. Who has heard about shot noise? Shot noise is due to the quantum nature of photons and electrons. It's you can say it's a stream of photons. In a photon detector, generates a stream of electrons. But these electrons and photons are bunching, so they're pockets. So if you have 1 million photons or 1 million electrons on average, the noise on that 1 million is the square root of that. So that's 1,000. So you measure 1 million photons plus or minus 1,000, the square root of 1 million. So that's your background noise. Now I have a background noise of 1,000 photons. And I measure now my very weak IR signal of 100 photons. No, it disappears in the noise. So you cannot just subtract. It doesn't work. It's very fundamental related to the quantum nature of photons. Okay. Let's go back to the advantages. So how do you want to do that now? You want to suppress the, do I have, did I show you? Yeah, I showed you this. That's what this is the, okay. I also had a, oh yeah, this one. So this is the Raman spectrum of silica. Silica is glass. So this is the material of which your optical fibers are made. So here you can see that as a function of wavelength shift per centimeters, this is the Raman signal generated in the fiber itself. And you can see that it has a very strong contribution. So silica fibers generated already, you can do a little bit, you can do a silica fiber that has a very low number of OH groups in it, and then you can reduce this effect, but basically this is what you need to fight. This kind of Raman background from the fiber. Okay, so with that in mind, so how would you define your, how would you develop your probe? One solution would be is to take a fiber bundle. You take the center of the fiber bundle as your excitation fiber. Then when the light comes out of this fiber, you need to have a very good filter to filter out all the Raman light. The only light that you want to come out of that core is your excitation wavelength. And then you pick up the Raman signal with the surrounding fibers. And even then, you have a problem because your original excitation light is scattered by the tissue, captured by the fiber, and travels again 3 meters through your fiber, generating these Raman signals. So even filtering the Raman, it helps already tremendous to filter out the Raman signal of your excitation fiber, but still your surrounding fibers pick it up. And this is the reason. So what would you need now at the tip of your center excitation fiber? You need a transmission filter that is very narrow and only transmits the excitation light. And so this here, this light is all blocks, and this would be your Raman shifted light generated in the fiber. And then for the detection fiber, you would like to have a filter that really blocks your original excitation light to avoid generating the Raman signal, the scattered light propagating back through the fiber and transmits all the light that is Raman shifted. And it's these filters that are very difficult to make because you need to suppress, sensitivity of suppressions of like 1 million, so 60 dB filter. And it's not easy to make. They exist, but it's okay. I want to show you one, let's say, really biomedical application. So in this research, the problem is heart disease, coronary arteries, where you develop vulnerable plaques. I don't know if you know what it is. Yes? Nobody else? It's the fact that due to a high cholesterol diet, in the coronary arteries, in the walls of these coronary arteries, you develop lipid pools. They're covered by the lumen of the blood vessel, which can be vulnerable or weak. And you have different versions of them. You have calcified plaques that cover the lipid pool, and you have fibrotic plaques that cover the lipid pool. The problem is if it ruptures, because then you get a release of lipids into the bloodstream. The lipids are thrombogenic, so they immediately form a thrombus, which blocks the artery, and that's where you have your heart attack. And people think heart attack is something that happens over time, because these coronary arteries become narrower and narrower. But a heart attack is a how do you call that? Abrupt event. Sudden event, rupture of the vessel wall, release of interlipid, thrombus, no blood flow. And here they try to determine the composition of these different plaques. And this is a non-atherosclerotic plaque, this is a non-calcified plaque, and this is a calcified plaque. And indeed, there you can see the different Raman signals for these different plaques. It never made it into practice because it is too difficult. It takes too much time to go from plaque to plaque to plaque. First, you have to find them, and when you have it, you have to do this measurement, and you can determine the difference between them. Brings me to the technology developed by General Motors cars. They have for measuring the temperature in their combustion chambers. So let's envision the following process, and I'm going to use now. You will learn how useful these Jablonski diagrams are, because with the 4 arrows I can explain the cars effect. Well, here and that's that Raman schedule. What happens here is that you have your incident photon, and it couples to a virtual state, and from that virtual state it couples down into an excited level of the molecule. Now you use the same incident object, it's a different photon, but the same wavelength of your excitation laser that excites it to an even higher virtual state, and from there it drops down into the ground state. And so what you've generated now is an anti-Stokes photon, a photon of a shorter wavelength. So why is this now beneficial? And if you look at this complicated process, and that's because it's what we call virtually background free. Background is in general fluorescence, where you convert a photon to something of a longer wavelength. But in this process, we have generated a photon of a shorter wavelength, and that's that's not an easy process, but it's also very background free. So that's the advantage of this. Sparse is I can't say truly background, because there are background effects in this technique, but the first order is background free. And you can do it with one pulse laser system. So the advantage is it's more sensitive, stronger signals than spontaneous Raman. Use something. No, I'm making a mistake. Sorry. This is my excitation laser, but at the same time, I provide a laser that has a slightly different wavelength that matches the transition from this excited state to the ground state. So you can envision now this to be a stimulated process. I excite from the ground state to this virtual level, and from this virtual level, with a photon coming out of my laser, I force it down into this excited state, and then I bring it up to a new virtual level, and then it decays spontaneously to the ground state. So it's this combination of two lasers where the wavelength difference exactly matches the energy difference between these two states. That is what we call coherent Raman scattering. It's more sensitive. You can do it in microscopes and scan much faster, so you can do nearly video wave imaging with this technique. It has the virtue of lower the wavelength is shorter, so no minimal present background. It's a two-focal process, gives also a resolution advantage. There's one disadvantage, and that is that you can only probe one vibrational level. You're really looking at this energy difference because you force it with the two lasers that you use to excite the system. You use two lasers with a fixed wavelength difference. Energy matches this, so you're basically only imaging the presence of this vibrational level in the molecule. So, I mean, I can't really well explain it, how it works, but the idea is that you have the plumb beam and you have the Stokes beam. These are the two photons that you provide. You can envision these two electromagnetic fields beating with one another. So if I look at the beat frequency of these two electromagnetic waves, that is the sum frequency, but also the difference frequency. So the beat frequency is now a frequency that matches the vibrational level of the molecule. Okay, then what is an advantage and why it is called coherent Stokes scattering, anti-Stokes scattering? And that's because each molecule is forced to have the same phase of vibration. You force the molecule to vibrate, and you force it with these two electromagnetic waves. That is the same for all molecules. So all molecules will have their dipole moment in phase with one another. Okay, and this is an important aspect, because what happens if I have an E field and I add a second E field to it? Now let's first do one E field, E1. What is the intensity that I measured based on this single E field?
E squared.
E squared. With complex formulation. Then I take E1 plus E2. Sum of two dipoles that are radiating. What is the intensity that I measure now?
E squared plus E1 squared plus E2 squared plus E2, and then the point is.
Yeah, so the intensity is E1 star plus E1 E2 star plus E2 E1 star plus E2 E2 star. And let's assume now that all these dipoles have the same amplitude, which means that E1 I'll make the result is 4 E1 star. And so what did I have in case of a single molecule having a dipole moment that was radiating? What was the strength or the intensity I was measuring? E squared. If I have two molecules radiating, what is the intensity that I measure? Sorry? 4 times stronger. Yeah, so 2 molecules 4 times stronger, 3 molecules 9 times stronger, 10 molecules 100 times stronger. So there is a tremendous advantage in this coherent anti-Stokes scattering, that all these dipoles that are radiating are in phase with one another, and I get this what we call coherent amplification of the intensity that I get. They are in phase, And this is the effect of these fields emitted by each individual molecule being in phase. And then the wavelengths are shorter than the excitation wavelength, which is also an advantage. I'll spare you derivation, but this is the important graph here. If I look at the molecular concentration and I look at the signal that I measure based on the molecular concentration, then for incoherent or standard Raman scattering, the intensity that I measure increases linearly with the concentration of my molecules. But if I do a Kar's process, that I make use of that coherence, then it goes with the square of the concentration. And so that is an advantage, except in this region. Yes.
Is it possible that the two lasers give like a multi-photon excitation?
Yes.
Is that background noise?
Yes. So if you would add, then you would generate two photon excitation. So you put the two 500 nanometer excitation laser. You would generate, let's say, let's say 1000 nanometer excitation laser. You generate 500 nanometer photons. You do the photon process, and they can create a background fluorescence which would interfere with this Nothing comes for free. Okay, then what you need to do for this process is you want to use pulse lasers. I dropped that. Sorry, but the Kar's effect goes with the intensity squared. And so when the process goes with the intensity squared, it's beneficial to use pulse lasers. And because in a short pulse, you have all the energy concentrated, and you take the square of that because you need the signal. So now you're looking at a system where you need a pulse laser and a second pulse laser, and these pulses need to overlap exactly. And when I mean exactly, the pulse lengths are on the order of 5 to 10 picoseconds. You have a rep rate of 80 megahertz, so it's a lot of the time there's no light, and only a fraction of the time there's a pulse there. You need to overlap these. When I was a PhD student, we worked in labs where we had two lasers, and they had the same cavity length. So that means the rep rate was the same, nearly. But even if you have the rep rate exactly the same, you still need to have these pulses overlap. So, you know, there were little tunable mirrors in the cavity that you could change over fractions of nanometers to make sure that the cavity length was the same, so they had the exact same rep rate, and that the output pulses exactly overlap. Well, that problem has been simplified tremendously with what we call parametric oscillators. So what happens in a parametric oscillator is that you send in a photon of a certain wavelength and you split it up in two. Let's say you used, I have to get my numbers right. You use a 500 nanometer excitation, and in the cavity you turn that into two photons of, let's say, 1100 and 900 nanometers. So you split that single photon up in two. The nice thing is that these two photons, 900 and 1100 nanometer that you've generated, are nicely in phase with one another. They come out at the same time, because they're generated at the same time, and they overlap very nicely with your excitation that you use. And so this whole synchronization problem has been solved with the parametric oscillator. The way it works in detail is you take a 1000 nanometer tunnel laser, you take a very small fraction of that light out. So you have here 1000 nanometer, then you frequency double the 1000 nanometer to 500. You use a parametric oscillator to create two photons, let's say 900 and 1100. And what comes out now, you have your 1000 nanometer here, and you can choose here between 900 and 1100. So that is now the wavelength difference, that energy difference that you need to excite this vibration in the molecule. Optical parametric oscillators. I made the argument of short pulses. That is because the effect goes with the intensity squared, so shorter pulses really help. The other thing is that your excitation spectrum needs to match the vibration levels of the molecule. And this might be a difficult argument, though I'm going to try and make it. So when I have a Raman line that has a width of 1 nanometer, of the 0.8 that we calculated, that is the width of the spectrum that's emitted by the molecule. It means that if I want to excite the molecule from its ground state in its higher level, I also can use a bandwidth around my center wavelength of about 0.8 nanometers. Let's say I need let's say I need 500 nanometers to excite the molecule. Certain realistic numbers much lower, but 500 nanometers to excite the molecule. But the molecule has an internal line width, so I can either excite it with 499 or 501, or 498 and 502. Right? So it can vary a little bit around it. But if I would use 600 nanometers, I'm not exciting the molecule. So there's a certain bandwidth within which I can excite the molecule. The other point is that if I use a very short pulse, it will not be monochromatic. If a monochromatic light means that it's one single wavelength, 500 nanometer and nothing else. But if I start to shrink the duration of the pulse and make it in the order of 10 picoseconds or so, the spectrum widens. It's not just 500 nanometers anymore. It will become, let's say, 498 to 502 nanometers. Okay, so the pulse length and the line width of the material need to match. And that is, in biological tissues, that means that your optimal pulse length is about 5 picoseconds. So that's the optimal, and that corresponds, that you can do the calculation. Your Raman band is about 10 centimeters, inverse centimeters. I've used that number before. If you calculate what spectral width you need to generate a pulse of 5 picoseconds, you will see that it nicely matches a line width of the laser of about 0.8 nanometers. So details, when you want to dive really deep into this technique, this is I showed you cars, and despite the huge advantages of, is it time already? Yes, great. So after the break, I do one more technique that is stimulated Raman scattering, and then I'll show you some examples of what you can do with it. And that's it.
Dipole excited.
Yeah.
Ja.
Maar daar dan dus een hele hoge houden nodig voor je leven. En dan zeg ik, geen rekening houden. Maar dat is dan al maar ik snap het wel.
Als jou een kloof heeft, dan ben je uitrekenen.
Ja, dan is spectrum steeds in de
Precies, ja, dus ik zie dat zijn Fourier van een paar en dat betekent een kort verschil breed uitgeeft. Maar wat het gevolg daarvan is, dat is de losse resonantie alleen maar 5 jaar want heel veel van die onderzoeken
ja,
helemaal niet. Dat is een argument.
ja,
Statische spectrum
nee, precies. Nee, ja,
nog beter uit.
ja, misschien was het inderdaad dan bij andere vakken in deze periode hebben. Ja, dat hoorden wij ook.
Oké, het laatste staartje.
Okay, laatste start.
Heel moeilijk.
Dan breek ik het af. So, last part. So, let's assume now that we have the following case. We have a pump laser and we have a Stokes laser, and we send them simultaneously in the sample. And let's assume we start with just air. What will we measure in terms of the intensity of the pump laser and the Stokes laser? It's air. This doesn't affect anything, right? So I'll measure basically the amount of power that I send into the sample. Now, what happens if there is a molecule with a transition vibrational energy that matches this difference? What will happen? What will happen with the pump? Will it get stronger or weaker? What happens in the normal Raman process with the incident light? What happens? You convert that incident light to? What happens in the Raman process? What do I generate?
Vibrational energy.
Yeah, in the molecule, exactly. And what happens with the emitted photon? Is it the same wavelength?
Now that it has less energy.
Yes, so longer wavelength, exactly. So you generate a photon with a longer wavelength. But what happens with the incident light? Will it be the same or will it be slightly stronger or weaker?
I would say the same.
The same. Well, that can't be because then you would generate a photon out of nothing. There's a Raman photon. So it is the incident photon that's converted to the Raman photon. So it's weaker. The incident light is going to be weaker. And what will happen with this beam? The Stokes beam. So my laser creates the Stokes light. I send two beams, pump and Stokes beam, with an energy difference that matches the vibrational level of the molecule. What will happen with the Stokes beam? It will get stronger, yes, because you convert one of these, incident photons into the Stokes photon. Okay, and what is the other nice thing of this? How likely is this process compared to the spontaneous Raman effect? Yeah. You read my body language. Okay. Yes, more likely. And I actually have a slide where I try to explain it a little bit. That we have this pump beam and we have the Stokes beam. And if you look at if you mix the two, we get the beat frequency. That's the frequency difference between these two beams that matches the vibrational level of the molecule. So providing pump beam and Stokes beam gives me a higher probability of exciting that vibrational state in the molecule. And when I do that with this laser system, in the absence of a molecule, nothing will happen. I will just measure my two incident beams that are reflected by the tissue or something. But as soon as there's a transition, the pump gets weaker and the Stokes get stronger. And so what do I do now? I start to modulate one of the two. I can turn off and on the Stokes beam. If I turn off the Stokes beam, this process is far less likely. So because when both are present, you force the excitation of the vibrational level. But if this one is not there, my Stokes beam will not be affected. So what I can do now, I can turn on and off, for instance, the pump beam or the Stokes beam, it doesn't matter, one of the two. And then I will measure a modulation on the other beam. If Stokes is on, the pump is going to get weaker in the presence of the molecule. if the Stokes, I turn it off, the pumping gets stronger in the presence of the molecule. If there's no molecule, turning on and off this Stokes beam has no effect on the pump. So only when there's a molecule, the pump beam intensity will fluctuate a little bit. And so that is called now stimulated Raman scattering. I stimulate the Raman transition and I measure the intensity on one beam while I modulate the other beam. Very nice technique because it's linear, very flexible. Actually, it has become the dominant technique over cars. First, 10 years ago, everybody thought that cars was the way to go for tissue spectroscopy, Raman scattering measurements. But this one is the winner now. It's basically the stimulated Raman scattering, modulating one beam and measuring the tiny fluctuations of the other. And so with that technique, let me show you then to close a little experiment that was done with it. So we're interested in lipids. Lipids are fats, and they have mainly CH2 bonds. And so that gives us a very nice Raman signal. And lipids are basically saturated with these bonds. So you get a very nice strong signal from these lipids. And what was the experiment? The idea was to use a zebrafish as a model system, and you're going to feed them a high cholesterol and a low cholesterol diet, and you were going to disturb their circadian rhythm. Circadian rhythm is their day-night pattern, and the idea was that if you disturb the day-night pattern, the question is, how do they convert their food into lipids, and do they do that at the same rate or not? It's difficult to image them with the fluorescence, but the idea was that you want to image the adipocytes, and that's a little storage in zebrafish that you can localize, and you can measure the size of the storage. And then we did that with the stimulated Raman scattering, basically determining the size of the lipid storage of these zebrafish. So you can do that with a normal diet, and a high-fat diet, and a high glucose diet, and you can measure then, what is the difference in the size of this storage after these fish have been on a diet like this. I hope I don't have the concluding slides. I'm so sorry. Let me tell you what happened. So it turns out that zebrafish, for which you disturb their circadian rhythm, turn their glucose and their excess food into larger fat deposits than zebrafish that are on a normal diet. And what's the implication? Well, it's far-fetched to make that big leap, but the idea is that if you distort this day-night rhythm, that affects actually your metabolism and creates larger fat storage. So one of the things that could have implication for people who work night shifts is that disturbed day-night patterns. People go on regular flights, crossing time zones, and it all affects your metabolism. And I don't know what your experience is, but I feel pretty miserable when I fly to the US, and I definitely eat too much. Okay, well, that wasn't a brilliant ending. Anyway, this is the end of my lecture.
I know you're excited.